Mamba 2 is out, and there's this massive paper. How many pages is it? It is 52 pages, well, kind of massive, that was released with it, and the authors basically developed this theory behind Mamba, SSMs, and their connection to transformers, which is very cool to see. So basically everything SSMs, transformers, and RNNs are all connected in some way, and they formulate theory on how these things are connected and how you can also leverage this connection to make an efficient algorithm as an SSM, as a transformer, or as an RNN, and how you get benefits from each one. So I don't know how long this video is going to be, but basically I'm going to go through like transformers and SSMs, and then transformers and RNNs and how they're connected, and then I'm going to go through the algorithm they use to make this efficient. So SSMs to start off with. And one thing, if you get anything from this video, basically it's that transformers are like quadratic, but there's all these linear methods, and there's no reason not to use a linear method now, such as like Mamba 2 or RWKV, even though RWKV is hard to read, but there's like no reason not to use a linear method. It's just more efficient to train, more efficient to do inference on, and just like you get about the same accuracy. So if you're going to train something, you should probably use a linear method. So to start off with, SSMs, and then basically how do you transform this into like a transformer. So SSMs are defined by the following. So like whenever I say SSMs, I'm going to be talking about Mamba. There's like S4, S5, and stuff that led up to Mamba, but Mamba is kind of like the big SSM everybody knows about, and that's the one they obviously use in this paper. So SSMs are defined by this recurrent, and these are state space models. Basically, you have H sub t, and I'm going to be using this as not a time invariant one. So the initial SSM was time invariant. This one's going to be not time invariant. And that just means that the parameters depend on time. So initially, you would have like your matrices that would just be static. However, we're going to parameterize these by time because that's more, or you get more performance out of it, or you get better accuracy out of it because it changes on time. So hidden state is going to be this, where H sub t is the previous hidden state and X sub t is the input. Y sub t is going to be CT transpose HT. And this is basically our occurrence relation. So our input is xt. It's just some token, you can think of it. And yt is going to be our output. So just real quick, what are the dimensions? A is going to be a n by n matrix, where n is going to be some dimensionality. So the dimensionality, I may write it as d, I may write it as n, or I may write it as p, depending on kind of the case, but all three of those are dimensions. B is going to be a n by 1, and C is going to be a 1 by n. And this is the original SSM formulation. Basically, it only worked on scalars. And what you would do is you would take a scalar, you would pass it through, and then you would get a scalar out. Or you would take a vector, pass it through, and get a vector out. So the initial one worked on scalars, and that's why we have scalars here. The B projection, you can think of it as taking this scalar, up projecting it to this high dimensional space. The hidden state works in that high dimensional space, and then down projecting it in that high dimensional space using the C matrix. So let's draw this out real quick. And I'm actually going to expand this to vectors. So instead of it being a scalar, I'm going to expand it to a vector because nobody uses scalars that encodes like no information. But expanding this to a vector, I'm just going to call this D for now. So instead of this being a n by 1, this would be like a n by d. So it'll just project up, where n is greater than d, likely. So draw this out real quick. So we have D. This is going to be some token at time t, so this will be xt. Now we send this through our B projection, so BT, and this will be a transformation entity. So we first up project our token. So this may be like the word the or something in the middle of the sentence, like, I don't know, I have no idea. Something in the middle of the sentence. So maybe the word the, maybe the word whatever word you want it to be. It's or a token. So we up project this token, and we take our past hidden state, and the past hidden state is just going to be a vector of size n, so ht minus 1, and we project that using the A matrix AT. That's just an n by n matrix, and we add these together. So add, and then we get our output hidden state. So that's just this update rule to the hidden state. This will be ht, and this will still be of dimension n. And what we can do is we can observe the hidden state to get our output at that time step. So we send this through CT, and this gives us our output vector, which will be of dimension d. And this will be yt. So this is kind of the original SSM formulation. Like I said, I made this a vector instead of a scalar. And also I made this time variant instead of time invariant. Now, this is just an RNN, pretty much, except it's kind of a fancy RNN where the structure part of the structured state models, or the state models, comes from the A matrix. And the A matrix was a structured matrix because if you just have this recurrence relation, since you're just doing an addition, you basically, this will diverge, obviously. Like if I just keep on adding vectors to this hidden state, this is going to diverge. Unless your vectors are like, unless you have the zero vector, unless you have vectors that are subtracting each other, but it's going to diverge. And the reason you have this A matrix is to kind of collapse or like refine how the information in H kind of stays there. So you make it such that the H matrix doesn't blow up and diverge as you keep on adding to this through this part here. And that's what A did. And that's just that, like, you don't want this thing to diverge, and if you don't add structure to it, it will diverge. And there were a lot of different ways to do that. The hippo matrix was one way. That was what they used in Mamba, I'm pretty sure. And that's why this was here. B and C, on the other hand, were parameterized by, those were your parameters, like a normal RNN. So that's the normal SSM. Now, what we can do is we can actually turn this thing into a quadratic form. So what we first need to do is we need to take this matrix and we need to convert it into a scalar. And the reason we're going to do that is because that will lead to a connection to an RNN, or to a transformer. So we take this matrix, which has structure, and we're going to turn it into an identity times a scalar. That's what they do in the paper, and this is just so we can make the connection. So this is normal SSMs. We're just going to make this transformation. So this will give us A1, A2, A1, A2, A3, A4, and so on, AN, and the rest here are zeros. So the upper triangle is zeros, and the lower triangle is also zeros. So this is what we're going to transform it into. It can also just be some value A times the identity, 1, 1, 1, 1, 1, 1. So we're just going to represent this matrix as a single scalar. And they mention down here that, like, to have structure, you need to be able to kind of reduce these matrices and be able to make computations in these reduced matrices. And the way we reduce this is by literally converting it from an n by n matrix to a single scalar, or to a vector of scalars. So we make this reduction, and that's where this structure comes from. So that's a big point they make. We need to have structure on this matrix. And the way they do that is by just making it a constant times the identity. That is the worst I've ever drawn. There. That's better. So let me draw this out real quick. So actually what we're going to do is we're going to parameterize it this way. over here, where we have some constant at times the identity over here, where this is parameterized by time, and yeah, it's just multiplied by the identity. So it gives us a scalar instead. So drawing this out, this basically gives us a matrix through time, which would look something like this. So we start off with A0, and what we're going to do is I'm going to formulate this attention matrix, or make it look like an attention matrix. So the initial scalar we multiply the hidden state by is A0, and then we multiply by A1. Now, the first hidden state is just going to be multiplied by A0, or by A0, so it'd be A0 times A0. And then the next time step, the hidden state is going to be multiplied, the A0 hidden state is going to be multiplied by A1, and it'll still be multiplied by A0. And that's because of this update rule here. Basically, this hidden state is going to be multiplied by all these A scalars ahead of it. So let's just draw that out. A0, A1, A2, A1, A2, and A2. So this is going to be time is equal to 0, time is equal to 1, and time is equal to 2. And this is going to be H0, H1, and H2. And this represents the scalars that are being multiplied by these hidden states. So we formulate this quadratic formulation of these scalars here. So if we go one more, A1, A2, A3, A1, A2, A3, and A2, A3, A3. This will be t is equal to 3, and this will be H2, H3. So this gives us the quadratic matrix, and this is kind of starting to look like normal attention. So using this matrix, we'll call this matrix, say, L. That's what they call it in the paper. Now, using this matrix, we can basically derive an expression for how to compute this in parallel. And they have kind of how you would get there, but basically the way we would do that is, it looks very similar to attention, is we would have y is equal to L. So the mask, this is basically a mask that you're going to apply. And what you're going to do is you're going to take the outer product of C and B transpose, and then multiply that by X, where X is going to be your inputs here. B is going to be all of your matrices, or all of your projections throughout time, and then C is also going to be all your projections. Now you may notice that this is the exact formulation of the attention mechanism, where the attention mechanism is instead L. Wait, that's B transpose C there. My bad. B transpose XC. So this is the formulation here, and I'll show more how this kind of comes about later. But yeah, this is directly related to attention, because this is essentially the attention formulation, which is QK transpose V. No, sorry, XV transpose. I'm getting my transposes wrong here, but it'll come apparent later. So basically, if we convert this A matrix here to scalars, we can get this matrix L here. And this matrix L is going to be kind of the mask. In attention, A is 1. But in the SSM case, we're going to make A some time varying number. And all that does, it means instead of having 1s here, you're going to have some other values here, which is still easy to compute. It's just masking. That's all it's doing. And from that, you can get this connection between attention and SSMs. So let me draw out how this would look. This here in the attention similarity case, because up here, like, it's not very apparent how this kind of connects to attention. You kind of have this in projection and you have this out projection. like it kind of connects because you have these the tokens, but it doesn't. It's not really apparent in this case. So let me draw it out real quick. This expanded recurrent form. So draw out this expanded recurrent form, and this expanded recurrent form is going to use the idea that we're using scalars here, and it's going to use the idea that we can transform these in projection and out projection matrices to basically our queries and keys, and we can transform basically X into we can transform this into query keys and values, as opposed to just having it being in projection or out projection. So if we do that, we get our B transposes here at time t. So this is basically this would be our keys. This would be our keys at time t. And this is going to be a matrix of size P. This will be a matrix of size N. And this will be our xt. These will be our values, P and N. Now what we do is we do an outer product between these two. So it'll be B transpose at time t, xt. And this gives you a P by N matrix. So this is going to be an outer product between the two. Just like, so basically we're doing this here. Yeah, I think I got that mixed up. This should go here. Yeah, okay. This is right now. I keep on mixing these up because C, B, and A are harder to look at than Q, K, and V. So this is right here. Basically, we're going to do this part here. Instead of C, B transpose, the inner product, we're doing the outer product of B transpose X. Forget about the mask for a second. We're doing this here. And this is what this outer product is. Now, what we do with this outer product matrix is we're going to add it to our hidden state. So our hidden state is basically going to keep track of the keys and values, or in the SSM case, it's going to keep track of the input tokens and the B projections. So we'll have this hidden state here. And this hidden state is going to be a P by N matrix, and this will be hidden state at t minus 1. Now we're going to multiply this hidden state by the scalar AT, which is just our matrix here. So at time 0, it would be A0, at time 1, it would be A1, and this gives you this compounding A here, because you keep on multiplying it as you increase the sequence length. So we multiply it by this, and it's actually the identity times that, but whatever. And then we add it to this. We add the outer product to this hidden state here. And this will give us our output H sub t, which is still a P by N matrix. Now, we also have these CTs here, and these CTs, or in this case it would be Q, or QT in the attention case, which is going to be a n-dimensional matrix, is going to be used to do this out projection. So we're going to do an inner product between the output hidden state. So this is going to be an inner product between all of the tokens from the past, compounded by A, multiplied by this Q matrix inner product, to get this p-dimensional matrix, or p-dimensional vector here, yt. So this is this SSM that this is an SSM where the special case of A being a scalar. This is that formulation. So let's take a look at kind of how these matrices, or how these things stack in the equations that they have. And this will make it easier to tie between attention, or linear attention, and SSMs. So we have HT is equal to BT transpose XT plus a scalar AT HT minus 1. And we have YT is equal to CT HT. This is just the hidden state recurrent, and this is the output projection for each hidden state. Now, if we look at H0, this is just going to be B0 transpose X0. And if we look at H1, that's just going to be... so we're going to add these new B and X vectors in here. So the outer product between the two. So this will be B1 transpose X1 plus A1, the scalar, or A0. I'll go with A1, multiplied by B0 transpose X0. Then we have H2 is equal to B2 transpose X2 plus A1, or rather A2, times B1 transpose X1 plus A1 B0 transpose X0. This is just taking this hidden state here and putting it right here. And this is equal to B2 transpose X2 plus A2 B1 transpose X1 plus A1 times A2 B0 transpose X0. So you can see this here, this compounding scalar here, and this compounding scalar is this part here. So if we look at time is equal to 1, I guess I would have to change this here. So t, 3, and 4. And I would have to increase these values by 1. But this here represents the compounding constants for the hidden state at that time step. So at H1, you can see it's A1, A2. Above it was A0 and A1. And then here it's just A2. Above it was just A1. So you can see this compounding. And as you add every hidden state, you compound each of these outer products more and more. And that's the structure that you add. And this allows the hidden state to keep on adding. You can keep on adding to it without the values blowing up, because these A values here basically make old information less valuable, which may have a trade-off, it may not, but that's pretty apparent here whenever we expand the hidden state out. So overall, the hidden state becomes S is equal to 0 to t. So h at time t is going to be equal to the sum. And it's going to be a sum of products. So it'll be sum of products, S is equal to 0, t minus s of as. So this is just going to be our compounding part here at time s. So here s would be 0, s would be 1, and I have t minus s because the farther back you are in time, so the less s's, the more compounding, or the more compound you're going to have. So be bs transpose x0, or xs, not 0. And this gives you your hidden state. And then to add yt, the out projection, is just equal to your hidden state here. So we can just copy the hidden state, and then it's the output projection times ct. And they call this the cumprod sum, which is the cumulative sum of products. So you have this cumulative product here, and you have this cumulative sum here. And if we allow a to be equal to 0, this is essentially going to be equal to the cumulative sum, or rather ht is going to be the cumulative sum from s to t, or from time is equal to 0 to time is equal to t. So cumulative sum from 0 to t of b transpose x. So basically it's this cumulative sum from all the past information, if we allow a to be equal to 1. If not, then you have to also take into account this product. This cum sum is going to be important because that's exactly how the attention formulation is going to come about. So let's move on. Now attention. So attention, which is all you need. Well, apparently not, because it's quadratic. So attention really isn't all you need. Or maybe it is, who knows. But attention is formulated as this here, in the general sense. So you have a function of some mask L of qk transpose times v, where these matrices here are, I think they formulated it as S by N by T, and T by P. I think that's how they formulated that. And basically, you have an inner product between your queries and keys, and an outer product with your values. So, or between these two here. Now, this is normal attention, where f is your softmax function. However, you can change this function, and perhaps it'll be worse, perhaps it'll be better memory-wise. We'll get to that later. So, in this case, like I said before, L is going to be this matrix here. And this matrix here is going to be in this case, it'll be an S by T matrix. S can be equal to T, it doesn't have to be equal to T. This is just more general. Same with N. N can be equal to P, but it doesn't have to be. And in this matrix here, you have this upper triangle, which is zeros. That is a terrible upper triangle. Let me redraw that. Yeah, that's better. So these are all your zeros, and then everything here is ones. Or this can be negative, or rather, this is negative infinity, and these are all zeros, depending on if you use an additive or a multiplicative, however you want to do it. But if we're adding it, if we're doing some transformation and we're adding it, then, or we're multiplying by it, then this will be all ones. Because in this case, we're doing a multiplication, we want to connect it to that. So this is ones and zeros, or ones and negative infinities. Now, if we look at this normal attention, let me draw it out. We have our queries here. We have our keys here. K transpose, and we have our values. So our queries are going to be a T by N matrix, our keys are going to be an S by N matrix, and our values are going to be an S by P matrix. Now, what we do is we do an inner product between the queries and the keys. So queries.keys, or queries.key transpose. So this will be a T by S matrix, where this will be the query dimension, and this will be the key dimension. And what this gives you is this gives you Q1, K1 in the top left. You'll have Q2, K1, where K is changing along this dimension, and Q is changing along the outer dimension. And this will be Q2, K2. And you keep on going until you get to, I think this will be QT, KS, and this will be QT, K1. So you can see how this is formed, or how this is coming about. You've probably seen attention before. So this will be all zeros up here, because we mask it with this by multiplying it. And you do the softmax along the rows. So softmax will be along the rows here. And then whenever you multiply it by the values, you get this output matrix here, which is going to be of shape T by P. So this output matrix here, which will be, say, Y. And this basically says every value here is going to be, this defines your linear combination of values here. So this would be a linear combination with just the first value. The second output would be a linear combination of the first value and the second value, and so on, until you get to the last one, which is a linear combination of everything. So this is everything put together here, except for softmax, which is just along the rows. So this is normal attention. Normal attention we all know and love, except it's quadratic, because we have to compute this matrix, and that assumes T is equal to S, but it's quadratic because you have to compute this matrix, and you have to compute that matrix because you have the stupid softmax function. And the softmax function, you cannot decompose. People have tried with kernel attention, but like the softmax operation, you can't really decompose it. There are things such as flash attention, which allows you to compute it in a more efficient way, but still you have the problem, like, it's natively quadratic. Now, the idea of kernel attention is hey, what if we take this f and we split it? So we can approximate f, which is equal to the softmax with a kernel. And this uses the kernel trick, so instead of y being equal to a function of qk transpose v, let's say we can approximate this. We can approximate whatever this function is here. Maybe that's softmax, maybe it's something else. Oh, I forgot the L. L of qkt and v. We can approximate it with L of some function of q and some function, I'll call it a different function, of k transpose, and then v. And the nice thing about this is, let's get rid of the mask for a second. The nice thing about this is this allows you to compute this part here. So instead of doing an inner product first, you can do an outer product. So let's see why that may be nice. So if this is s by d, this is d by s, and this is s by d, then if we do this operation first, this will give us our quadratic s squared in memory, in time and memory operation. However, if we group it the other way, like this will give us a d squared in time and memory. And then it's linear in s. So doing it on the left first is going to be it's going to be of the order s squared. I guess s squared d. However, if you do it on the right first, then this gives you sd squared. So this is why it's nice to kind of turn it into a kernel instead. It allows you to turn this into a linear operation. Now, if we do that, and we do it in a specific way, then this can relate to, this basically gives you all the linear attention things you've seen. So some linear attention are like, some linear attention mechanisms say, what if we turn this into a ReLU? Probably your first thought. Does that work? It works fine. What if we turn this into, say, the exponential function? Another good old function that everyone always uses. So you can turn this into like any function, and it could work, it could not work. There are obviously some trade-offs. The expressive power isn't going to be as good as your softmax function, but it allows you to compute this in linear memory. So what linear attention does is it takes this and we just turn it into this kernel method. So linear attention. So we're going to let's say we choose two functions for this. Maybe we choose ReLU, maybe we choose the exponential. There are, like I said, there are multiple linear attention functions out there that have been used. Maybe you even use SciLU if you want to mix it up. But let q hat be equal to the function of q, and let k hat be equal to the function of k. And like I choose psi and phi just because they can be different functions. Then what we have is we have y is equal to L of q k transpose v. Now, this is with the mask. Above, this was without the mask, and it was super easy. You can just say, I do right first or I do left first. However, this is annoying to deal with. But what you can do is you can redefine this as a cumulative sum. So y is going to be equal to q times the cumulative sum of your keys and your values. And basically, this is the formulation we had. It is very similar to this formulation up here, the cumulative sum. And this is going to be how we're going to make the connection. So this can be represented in the same diagram as above up here, except you're going to change, this is where the keys and the values come from. So the cumulative sum below allows us to redefine this diagram such that you have your keys here, your values here, and your queries here. And this is because you have this cumulative sum operator. Notice how we ended up defining the SSM as a cumulative sum, assuming we make this 1. If we make our A's 1, then we have this cumulative sum operator. And this cumulative sum operator down here is the same as linear attention. And if we just redefine our matrices as Q, K, and V, instead of B, X, and C, then you get the exact same diagram, and you get the exact same formulation, where this is 1. And that means that with our SSM, which is an RNN, and our linear attention mechanism, which is our quadratic attention mechanism, are the same thing depending on how you define your functions here, or depending on how you define your A values here. So there's this connection here, and this connection shows that they're basically the exact same thing depending on how you define your functions. And this is the connection they kind of show. The connection was already there between RNNs and attention, but they show that you can connect this to SSMs with the choice of a mask. Instead of it being 1s, you can choose it to be some compounding function. And they show that down here, that there is a direct 1-to-1 correlation that you can achieve, which was shown over here via the cumulative sum right here. So there's this connection here between the SSM and your what they call structured mask attention. Now, the thing about this is your masked attention has this mode here. This mode here is super efficient parallelly. Like, you can compute attention super fast because of how the GPUs operate on matrices. It's just matrix multiplication, multiply by a mask, one more matrix multiplication. Like, that is super fast on GPUs. However, RNNs are super slow on GPUs, but they're super memory efficient. So you have this trade-off. You can either have this parallel method, which is super fast, but super memory inefficient, or you can have this sequential method, which is super inefficient. Like, it's not fast, but it's very, very memory efficient, because all you have to do is store the hidden state. And the hidden state is just this D by D, or N by N matrix. So you have this trade-off. Now, what they do is they say there are these things in the middle, like linear attention, and retnet, and transnormer, or gate loop. I've never heard of transnormer, that are in the middle, where they're not completely parallel and they're not completely sequential. They're in the middle, and it makes a good trade-off. So what Mamba 2 does is it basically it finds something in the middle that's both memory efficient, so kind of sequential, but also super parallel. So, or also somewhat parallel. So it's still fast to compute. Because you have to have something that's fast and memory efficient to have something that's really good. So that's what Mamba 2 kind of finds. So to get there, we have to define this M matrix, which is defined over here. So this M matrix is going to be defined as this. It's basically going to take into account the keys, the queries, and the compounding A values. And this is just going to be a way to organize the information so that we can compute it efficiently. So let me write it out in both ways. So we want this M matrix. So this M matrix, basically we already have defined, I'm going to define this in terms of C and B. We already have defined our Y as a masked version of CB transpose, or as QK transpose multiplied by X, which is equal to mask of CB transpose, that's V, multiplied by X, which is equal to M times X, which is equal to M times V. So what we're going to do is we're going to define this part here as our M matrix. And we're going to do that because they form an algorithm around M. So let's formulate that. So the matrix is going to look like this. I'll define it in both ways so that it's transpose. So that's not hopefully less confusing. I like to look at things in terms of QK transpose because I've seen attention a lot more than SSMs, but CB transpose is just as equivalent because we have this equivalence relation we defined above. So this matrix here, we'll start with Q1, K1, A1, and then Q2, K1 transpose, A1, A2. And I'll just define this up to Q3. So Q3, K1 transpose, A1, A2, A3. There we go, I fit it. And then we're going to have Q2, K2 transpose, A2, or A1. No, A2. Then we're going to have Q2, K2 transpose, A1, A2. So let me just write this out in red. And then finally we're going to have that'll be Q3, Q3, K3 transpose, A3. That'll be A2, A1, A2, A3. There we go. So this is our M matrix here, where our queries are going to be changing on the columns. So this will be our queries, or on the rows, and our keys are going to be changing on the columns. So keys are changing on the inner, queries are changing on the outer. And this is going to be our T by S matrix, or S by S matrix. So this is going to be our big quadratic matrix that we're working with, because this is the inner product that we're working with. Not the outer product. And the reason we can't work with the outer product is because we have this stupid mask here. So this would just be multiplied by V in the end. But yeah, this is M, which you would multiply with V1, V2, or that would be V2, and V3. And the reason I write the subscripts in different colors here is because the values correspond to the keys. So this isn't just keys are changing along this dimension, but the values are also changing along this dimension. So this first column here corresponds with K1, but it also corresponds with V1. Same here, it's K2, V2, and K3, V3. And that allows you to compute this more efficiently. Because the keys and the values are changing together, the queries correspond to the outputs. So this first part here would correspond to Q1, but it also corresponds to Y1. This one corresponds to Q2, but it also corresponds to Y2, and this one corresponds to Q3, but also Y3. And of course, this is your diagonal, so this is zeros, or negative infinities, however you define it. And this has a direct relation with the SSM if we define this to be B and X rather than K and V, or if we define this to be C as opposed to Q. So this is our M matrix that we're defining. Now, what they do with this M matrix is they say, we're going to break this up into blocks. So we have these two blocks that we're going to define, and we're going to define it as these, what do they call them? They call them the diagonal blocks and the low rank blocks. So you have these diagonal blocks here. In this case, it's a 9 by 9 example. So in this 9 by 9 example, you have this, 9 by 9 matrix. And these parts here are going to be your, I guess I'll draw it in highlighter. These parts here are going to be your diagonal columns, or your diagonal blocks. And these diagonal blocks are going to be computed in parallel mode. Now, the reason you compute these in parallel mode is because you cannot decompose these matrices. And the reason you cannot decompose these matrices is because you have this masked part here. And if you didn't have the masked part there, then you can just compute it like we're going to do with the low rank parts, which are these parts here. But since we have the mask there, it's more efficient to just compute them in parallel mode. So that is easy. You just do your normal parallel attention mode, just in terms of the block instead of in terms of the entire matrix. Now, instead of computing the whole thing in parallel mode, we're going to use recurrent mode to compute these low rank blocks here. So we have this parallel mode for the diagonal, and then the off diagonal are going to be computed in recurrent mode. And we're going to use recurrent mode because you actually get, it's low rank for a reason, and we're going to see why it's low rank. But this low rank feature makes it much more efficient to compute in sequential mode than it does in parallel mode. And this means that it's going to be better than computing everything in parallel mode, and faster than everything, or better in terms of memory, and faster than everything being computed in sequential RNN mode. Now, what we're going to do is we're going to break this into blocks. So in this case, they break it into blocks of 3 by 3, but you can change your block size to whatever you want it to be. In the example I'm going to show, it's going to be 3 by 3 because I don't want to kill y'all's sanity by drawing out a larger than 3 by 3 matrix, and I don't want to kill my sanity by drawing a larger than 3 by 3 matrix. So let's do an example. So I said these diagonals are easy. This is just QK transpose, or the SSM equivalent. These off diagonal blocks are the low rank ones, which are kind of unintuitive. It's also unintuitive because the notation they have is quite terrible. So I'm going to write it out using their notation just so you can relate it back, but also trying to explain it as I'm going through it, so that hopefully it makes sense even though the notation is bad. Yeah. So let's start off with, I'm just going to do this block here. And this works for every other block. It's the same computation. It's just, how do you compute it? It's the same computation. It's just different indices. So this block here is going to be computed, so they decompose it already here. So what we have is we have C3 transpose, A3 to 2, C4 transpose, A4 to 2, and C5 transpose, A5 to 2. And then in the middle we have A2 to 2, and then here we have B0 transpose, B1 transpose, B2 transpose, A2 to 0, A2 to 1, and A2 to 2. And this is transposed here. So this is equivalent to this here, and I'm going to show that. Here. So this here is going to be so our C matrices are going to be 3 by n, so it's block size by n. Our A matrices are going to be n by n, because this is going to be our identity times the scalar. I'll mention what these annoying indices mean, and this is what I mean by bad notation. This is bad notation. This is terrible. I hate this notation. It's so bad. The rest of the paper is amazing. This notation is just bad. So this gives you a 3 by n matrix. This is going to be n by n. So n by n. Multiplying these together gives you 3 by n. Now here, B transpose is going to be 3 by n. And this A matrix is going to be n by n. And you transpose that. And multiplying this together and transposing it gives you a n by 3 matrix. And multiplying these three together gives you a 3 by 3 matrix. So the shape works out. Now, do the values actually work out? Real quick, before I go through this, how this actually leads to, just showing that this is equivalent. This A indexing, which looks like crap, is equivalent to, so AJ to I is equivalent to AJ times AJ minus 1 times all the values between there and I plus 1. It just is. So yeah, don't ask why. That is how they defined it. Yeah, I'm not going to get into how annoying that notation is, but that is the definition of these here. So these indices here mean a product, and it's a product between the values in this here. So this would be 2 and 1, A2 and 1, and this would be 2 and itself, so just 2. So yeah, and we're just going to combine these indices. So yeah, it's just a product. Now let's go ahead and write this out. So the first thing we can do is we can move A into here. So we'll do that real quick. So C3 transpose, C4 transpose, C5 transpose. So I'm just going to copy down the C matrix here, A4 to 2, A5 to 2. And what we're going to do is we're going to multiply this by, so we're going to move this into here. And we're just going to do that by changing the indices on A. So let's do that. We have B0 transpose, B1 transpose, B2 transpose, and this will become A2 to 0, so same thing. Oh, sorry, I moved them in the wrong place. These, I'm going to move them into the left matrix, actually. So this will become A2 to 2, multiplied by A2 to 2, and A2 to 2. And doing this basically will give us, this will give us A3 to 2, so it'll stay the same. This will give us A4 to 2, and this will give us A5 to 2. So that's what that gives you. And then this will be multiplied by the same matrix here. So this will be the same matrix. Basically what this does is it adds the 2 part. So like this notation basically says that it doesn't include 2. This basically makes it include 2. So I guess this would be 1 now instead of 2, but that's just because the notation is bad. So this makes it so that it includes 2. So now that we have that, we can write this out by just multiplying this row and column wise. So I'm just going to do that for the first few. So if we do this multiplied by this, that'll give us C3 transpose, A3 to 2, or A3 to 1, multiplied by A2 to 0, multiplied by B0. And this will be, this will give us A3 to 0. So basically all the values from 0 to 3, which is just going to be A0, A1, A2, A3. And that's going to be our first part right here. Now what we're going to do is we're going to multiply B0 by C4. So that'll be C4 transpose, A4 to 2, A2 to 0, and B0. So this will be A4 to 0 and B0, and so on. And as you can see, this is formulating, or this is creating this matrix here. So you can trust me on this, or you can go ahead and multiply these out if you want, but it does lead to this equivalence. This decomposition leads to that equivalence. All right, so now we have this equivalence. What does that give us? Is this useful at all? It is. It is very useful because we can define this as a recurrent neural network. So let's define this as a recurrent neural network. I'm going to bring this down here. Yes, I'm just going to use, I'll use a slightly different version of this, but it's just going to change the indices a little bit. So just so you don't overfit to this example, I'm going to change the indices a little bit. So I'm going to change this. Basically, we're going to do a recurrence on 2 parts. We're going to do a recurrence. Basically, we want to compute these 2 blocks here. Now, like I mentioned up here, I mentioned it in many places, but basically, our queries change along the rows, and our keys and values change along the columns. The idea is we're going to have a recurrence where the keys and values are going to basically add on top of each other. And that's because we've defined the recurrent neural network up here in terms of the keys and values, or in terms of B and X. Oops. So we're going to have a recurrence on B and X, or on the keys and the values. And this also includes A, so we have to deal with A. So I'll show how that works. So basically, let's look at this part here. Let's compute this part, and it's basically gonna be going down. So let's take this here, and let me just copy it. So we have these. This will be our first block here. That'll be this upper block, and this lower one will be the second block. So let me change the indices. Notice that only as we go down, only C changes, and only A changes. So this becomes 6 to 5, 7 to 5, and 8 to 5. And this becomes 5 to 2. So notice how, as we go down, the queries change, and that's because they change along the rows. So let me draw out how we're going to do this. They form an algorithm in this way. So the first step to the algorithm is to take... So one thing to notice is that the B values do not change. So this is the property that we're going to use. The B values do not change. And you also have the X values here. So this will be times X0 times X1 times X2 times X0 times X1 times X2, because the values don't change, or the X inputs do not change. So what we're going to do is we're going to start off with our B values, or our key values. So this will be B or K. And we're also going to have our X values, or our value values. So this will be X or V, depending on if you look at this through a attention or a SSM perspective. So this will be B, and this will be the B values from 0 to 2. And these are transposed. And these will be the X values, and these will be the X values from 0 to 2. And these are not transposed. So this is going to be a matrix that's n by 3. This is going to be a matrix that's 3 by p, where this is the dimension here. So this is going to be our outer product matrix that we're creating. So step 1 is create this outer product matrix. So this will be B from 0 to 2, transpose X 0 to 2. This will be our first part. And this is on the block. So this is going to be the first step. And this is going to be an n by p matrix. So step 1 is compute the hidden states. And let me go over to the code to show that. We'll go over the code in a second, but it's this part here. This is step 1 is computing the hidden states. And this is after you've broken it up into blocks. So step 1, I guess, would be break into blocks, and then step 2 would be compute the hidden states. And to break into blocks, all they do is they say, we have this length dimension, so this will be your sequence dimension, your sequence length, and you break it into C blocks of size L, or of size B, however you want to define it. And here they define it as C blocks of size L. And then after that, you compute this matrix here. This also includes the A values, but I don't know how to write them in a nice way to include them here, so I'm not going to write them. So this is going to be our outer product matrix, just like we saw in the recurrent neural network that I drew above. And this is step 1. Now step 2 is going to be, so up here we have these 2 sets of outputs that we want. So we have the shared space here, and we have this shared hidden state. However, we want to basically create 2 hidden states, one for this here, and one for this here. And the way we're going to do that is we're going to basically multiply it by this A matrix. And this A matrix basically has this divergence where you have a shared hidden state here, but you basically split your hidden state between A because they're different. So you just multiply by the hidden state, and this gives you your two different hidden states. One for your 0 to 2 outputs, and the other for your 0, 1, and 2 outputs. The other one for your 3, 4, and 5. 0 to 2, or 1 for your 3, 4, and 5, and 1 for your 6, 7, and 8. So you multiply this here. I'll just copy it, make it faster. So this will be our first set of outputs here. So this is still an n by p matrix. You just multiply it additionally by A. So you would now have A from 2 to 0. And it actually wouldn't be A from 2 to 0. It would be A from 2 to 0 for your first matrix, A from 2 to 1 for your second, and A from 2 to 2 for your third, depending on the B values here. Or depending on the A values. But anyways, get the point. But over here, the A values would change. So this would actually be from 5 to 0. This would be 2 to 0. And the reason you do this is because these queries are later, and because they're later, that means that there's more A values that accumulated in there. And that's just intuitively, basically you can think of that as your current state basically capturing more information. And as it captures more information, the A values compound more. So that's how you can think of this. So step 2 is multiply by the cumulative A values to get the two hidden states. This gives you your two hidden states here. Now, step 3, your final step to get your block outputs, is to multiply by the C values, or the query values. So we have our query values here, which is a 3 by n matrix. So this will be our queries, or our C matrices, and this will be 3 to 5, while this will be our C 6 to 8 matrix. So this will be 3 by n as well. So these are our two different output C matrices that we're going to multiply with. And this gives you a 3 by p matrix, and this also gives you a 3 by p matrix. So you multiply these together, and this gives you your output matrices. Note that these are not 3 by 3 matrices, they are just 3 matrices. They don't have a second dimension, and that's because we multiply by the values here. So we're already doing this post-output projection at the beginning step. We're not doing it at the end step. So that's why we result in one dimension of size 3, not 2. So this is what we end up with, and this is y 3 to 5, and this is y 6 to 8, which corresponds to the outputs for this block and this block here. So that's what we do, and we basically do that for every block. And we use this shared part right here going down. So going down. So that's the idea. Compute these using in parallel mode, compute these in sequential mode by sharing the B values as you go down. They have this diagram here. Basically, you have these inputs. You use this right projection, which is the first step, step 1, computing the hidden state, by multiplying by the B and X values. So that gives you, or multiplying by the B values, that gives you your hidden state. And then you get this output projection here by multiplying by the left values. And the left values basically give you your output for that block. And you can go from hidden state to hidden state by changing the A values, which is essentially adding more of these multiplicative terms. So that goes from hidden state to hidden state. Let me move this over. And you also have these X values, which are immediately projected in sequential mode by the C values, or by the C and B values, to get your diagonal ones. And all you do is you just add these together. So this here, if you add along this row here, this will give you your output at 3, and this will give you your output at 4. So y4, y3. So you just add the outputs together, and then that gives you your actual output. So there we go. Right factors can be thought of as like an inner projection, center factors as a recurrence, and left as outer. So right, center, left. There you go. And that's the algorithm. Here they formulate it in code if you want to read through it. The code was a little unintuitive. It would probably be easier if you like step through it with actual code, but just looking at it, it's nice that they give code though. So basically what you do is you start with these A, B, and C matrices, A, X, B, and C matrices, you rearrange them into the blocks, C blocks of size L, along the sequence dimension, and this here is computing the diagonal. This here is doing the in projection using the B and X projections. This here is kind of the recurrence, computing the hidden state, and this here is computing the output state using the left term, and this here is just adding all the terms together to get your final outputs. They also have this here. Basically, like if you have multiple GPUs, you would want to pass the hidden state on so that the next GPU can use it. So you can initialize the hidden states such that that can happen. So there we go. That is Mamba, the Mamba 2 algorithm. Now, what is Mamba 2? Complexity. I forgot about that. So complexity for this algorithm is, this is a good diagram here. Basically for an SSM, so n is the dimension, and s is or t is the sequence length. So for an SSM, or for attention, we all know that this has a like the training flops is quadratic and the inference is linear. However, for an SSM, and the state size is t. So that means you store every value, For an SSM, we have a state size of n, and that's just the hidden state size. For training, it's linear in terms of time. It's quadratic in terms of the hidden state, and it's quadratic in terms of the inference flops. Or it's linear in terms of, it's constant in terms of the inference flops because it's an RNN. All you have to do is store the hidden state. While in attention, you have to store all the value, or all the past keys and values. If you use KV cache. If you use the quadratic method, then it's quadratic. For naive, so basically this is linear. This is a whole order down over attention. Attention is quadratic and linear. Quadratic for training, linear for inference. SSMs are linear for training and constant for inference. So it's basically a whole T down. They also say that their SSD approach, which is the new approach they add, the new algorithm, reduces this from n squared to just n in terms of the memory. So there we go. It is much more efficient in terms of memory and inference. Now, the actual architecture, basically they take Mamba 1 and they change like 3 different things. So normal Mamba is this is like your SSM part. So this is the algorithm described above. You have your input projections. This is kind of like a skip connection. But the main part's kind of right here. What they do is they combine the A, B, X, and C projections into one matrix like you do with Q, K, and V. And that's just because it's more efficient to compute. The next thing they do is they have a normalization part here after the multiplication. And the third thing they do is they say, oh, we use one head for B and C. And that's just to make it more efficient in terms of memory and in terms of speed. So that's what they change from Mamba 1 to Mamba 2. And then you have this out projection. So up project, down project, it's just normal Mamba. And then you have this convolution here, basically to, I guess, mix up the sequence length a little bit before you pass it through the SSM module. Okay, on to multi-head, different multi-head styles. So they talk about why they do that here. So there are multiple multi-head styles. I think they go with multiple input SSM. But basically you can have a whole H heads for the queries, keys, and values, or you can remove some of the heads on the keys and values, or on the keys and queries, and that's what they do here. They just make it one head on the keys and queries. They mentioned some other things to make it more efficient, but yeah, I don't think that's that big of a deal. And grouped head patterns. Yeah. You can do weird stuff with heads if you want by removing some. All right. So another thing. So they have this tensor parallel framework. This is what I was talking about earlier. If you want to take a hidden state from one GPU, or if you want to basically share this information between GPUs, you can take a hidden state and you can put it on the other GPU, and you initialize the algorithm to this hidden state. And this allows you to compute on multiple GPUs. So this algorithm is very nice for multi-GPU. Softmax attention sucks for multi-GPU. It is annoying to do. But an RNN, you can imagine, wouldn't be that bad as long as you can pass the hidden state in between. Like if you have one GPU do a part of the RNN and the other GPU do a part of the RNN, all it has to do is pass the hidden state and hold on to the query keys and values, and then it's fine. But if you have attention, then you have to worry about this quadratic matrix that you have to compute, and that's a pain. 8.3. So one cool thing about Mamba, because it's an SSM, or because it's linear, or because it's an RNN, is they mention here, with SSMs and Mamba in particular, we can handle variable sequence lengths by simply treating the whole batch as one long sequence and avoiding passing the states in between individual sequences. This is equivalent to simply setting A equal to 0 for tokens T at the end of one sequence to prevent it from passing information to token T plus 1, which belongs to a different sequence. So basically, you can just have this hidden state go through the entire sequence of all your sequences in your batch, where the hidden state is reset to 0 whenever it reaches a new part of your batch. And this way, you don't have to worry about padding at all, which is nice because that means you don't have to worry about computing things that are useless. So this is a cool thing that they mention. Flops. As you increase the number of flops, the perplexity goes down, and for Mamba and Mamba 2, it's slightly better than a transformer on this graph here, so on the pile. It probably isn't. I don't know if it's a ton better. We'll have to see if it actually is. They show it performs really well on benchmarks compared to Mamba, or it performs better than Mamba, and it performs really well compared to transformers like Pythia, RW, other linear methods like RWKV. And they mention it has really good scaling properties. Like it's just normal benchmark stuff. Of course, they get state-of-the-art and everything. However, it's probably going to be a trade-off. They mentioned speed benchmarks. It's fast because you can do it in you can use this sequential method as opposed to you can use this parallel and sequential method. And more perplexity metrics. So yeah, if you're curious, you can look through the evals they have. I'm not going to go through them. I think they also have some more down here, but that's the basic idea of Mamba 2 and the algorithm behind it. You can formulate this. Transformers, SSMs, and RNNs is the same thing, or through the same context. So you can convert between the three, and you can basically formulate this algorithm that uses the efficiencies from all three to have this really nice algorithm that's both sequential and parallel. So it's fast and it's memory efficient. And this gives you this algorithm, this SSM algorithm, and you can create Mamba 2 using their Mamba 2 blocks, which are supposedly really, really good. The main thing I get from this paper is that you should be using linear methods. You should not be using these quadratic methods. And that SSMs, transformers, and RNNs are not so different than one may think, because you can relate all three of them. So yeah, we'll see how Mamba 2 performs whenever people start experimenting with it.